Okay, good morning everyone. I'm Ricardo Figueiredo, Commissioner Early Career Representative, and it is a great pleasure to introduce to you Dr. Hidetoshi Katori, a distinguished professor at the University of Tokyo and the chief scientist at RIKEN's Quantum Metrology Lab. Dr. Katori is a pioneering figure in timekeeping, renowned for inventing neutral atom-based optical lattice clocks. In the early 2000s, Dr. Katori's groundbreaking work led to the creation of ultra-stable optical clocks, which have revolutionized timekeeping, geodesy, and fundamental physics. He demonstrated these clocks with strontium, ytterbium, mercury, and cadmium atoms, and his precise measurements of frequency ratios among these elements paved the way for adopting neutral atoms optical lattice clocks as the secondary representation of the second and the primary candidates for the redefinition of the second in the International System of Units. Dr. Katori's contributions expand beyond the lab. He recently demonstrated a compact, transportable optical lattice clock for field experiments, including a notable geodesy demonstration at the Tokyo Sky Tree, showing centimeter-level height difference measurements using Einstein's relativity. His innovative spirit also led to the proposal of the Internet of Clocks for geoscience applications, including earthquake monitoring. His group is also pioneering research on thorium-based nuclear clocks, with significant achievements in measuring the energy of the 229th thorium nuclear clock isomer. Dr. Katori has led prestigious projects such as the CREST and the Hirato Katori Innovative Space-Time Project. His numerous awards include the Breakthrough Prize in Fundamental Physics, the Misius Quantum Prize, and the Onda Prize, among many others. Please join me in welcoming Dr. Hidetoshi Katori. Can anyone get Dr. Hidetoshi Katori mic'd up, please?
Thank you very much for a kind introduction. And I would like to thank the organizers for inviting me to this wonderful island and beautiful conference. So I will start. So the title is this, and I will actually speak optical lattice clocks as the as sensors for relativistic spacetime. It's good to have more people there. So we want to think about real-world applications of the state-of-the-art atomic clocks as accurate as 10 to the minus 18, which lose or gain 1 second over 30 billion years, which is 2 times the age of universe. It's so accurate, so you will wonder how to use that. One of the applications is that gravitational redshift makes clocks as a new sensor. I will discuss in detail later. Gravitational redshift gives 10 to the minus 18 fractional frequency shift for every centimeter. Then our concern is how quick can we measure frequency, or how we can downsize the clocks. This is the last topic of my talk. So during past days, I found there are researchers from a diverse area of radio science. So I will start from the very basic thing for atomic clocks. So atomic clock rely on the constancy of fundamental constant. What we do is measure transition frequency from the ground state to the excited state as precise as possible. Then stabilize the laser frequency to the atomic frequency. The long coherence time of the atoms gives narrow spectrum, which is less than 1 Hertz. Then quantum noise matters. To measure the line center very accurately, we need to measure many atoms to reduce this uncertainty. So this is the beginning of the idea to think about optical lattice clock. We proposed the clock scheme in 2001, which is purely curiosity-driven way. By using a standing wave of light, we can trap many atoms to know the center frequency better in this way. In 2014, we realized agreement of 2 optical lattice clocks at the level of 10 to the minus 18. Then we started to think about compacting the optical clocks, make a rough-sized machine to a transportable ones, which is to use optical clocks, for example, for relativistic geodesy. Because we have 2 clocks, then we can easily lift one of the clocks. According to the Einstein's theory of relativity, the upper clock ticks faster. Then seeing is believing. We compare these 2 clocks by slightly lifting up one of the clocks by 1 meter. It's a very early demonstration. After making our clock, so we measure the height of 1 meter and compare. It was a 6-hour measurement, and we measure the beat note of these 2 clocks. When I say clock, it means a clock's oscillator frequency. So this shows clocks agrees very well because the bit node is 0. This is raw data, but if you average it for 1 minute, then you will see something. And average down to half an hour, then you will see a straight line. The clocks at the same height agrees at the level of 10 to the minus 18, while the upper clock ticks 47 millihertz quicker than the reference clock. This shows that the gravitational redshift can be measured by clocks quite easily. And with this, 18-digit accurate clock will resolve 1 centimeter height difference of clocks. And this can be a new sensor. What we are doing is like this. We have a reference clock, which oscillates at 429 terahertz. And these numbers are described by SI with 16-digit numbers. By lifting up 1 meter, then the clock should tick like this. And the difference is this. The thing is that SI describes these 16-digit number, but this is varied in their definition. This is a motivation for the definition of the second, up to with optical clocks. And the definition is planned in 2030, and candidate scheme or elements will be decided in 2016. This is a roadmap for the definition. So, accurate clocks made Lattice melting clocks a reality. Space-time is curved by gravity as described Einstein's theory of relativity. This is Lattice's famous painting, inspired by the Einstein's theory, which was drawn in 1931. So, in 90 years afterwards, now we are realizing such clocks. And once such clocks are available or commercially available, what will be the roles of clocks in 10, 20 years? So I want to discuss this in the last part of the talk. So we will discuss the 18-digit accurate atomic clock, science and applications. Why atomic clocks? When I was asked, I said, to explore extreme precision. Never measure anything but frequency is the word from also shallow. And now the world is really like this. Frequency is the physical quantity that can be measured with by far the greatest accuracy. I will introduce the idea for an optical lattice clock briefly. Then I will talk about its applications. And we are now pushing our lab experiment to black box in collaboration with industrial partners and make a very compact atomic clock. So many people discussed in this conference SI, the cornerstone of science and technology. Speed of light is defined in 83, and then measurement of length is replaced by a measurement of time. This is used for the GNSS system quite conveniently. And now the Planck constant is defined to replace the mass reference. Then, if you think about the equivalence of mass and energy, mc squared is energy, and if you divide it by Planck constant, then mass measurement can be a frequency measurement. So all the measurement can be a frequency measurement. This is what also Charles said. And now, SI second stands at the top of that definition, and the only measurable quantity. So there was a famous old paper, 1960, whose title was Apparent Weight of Photon. I will introduce this paper to explain gravitational redshift. So atomic clock measure the transition frequency of atom very accurately by exciting the ground state atom to the excited state. Then atom absorbs photon energy, and excited state atom can be a bit heavier by energy of a photon. And when you lift up the atom gets the gravitational potential energy, mass times gravitational acceleration times height difference. When the upper atom reduces to the ground state, the atom emits a photon. Then photon's energy or frequency is a bit higher, which is a gravitational potential energy for apparent weight of a photon. So this explains gravitational redshift of 10 to the minus 18 per every centimeter. And our clocks serves as a gravitational potential sensor. So my field is atomic physics, which manipulate atoms as precise as possible. And some basic ideas for the laser cooling and laser trapping atom is like this. Laser cooling is done by shining a resonant photon to the atoms. By absorbing the light, atom changes its momentum. And with this scheme, we can cool the atom down to a microkelvin or further below. For such outer core atoms, we can apply a laser tweezer technique. When you apply laser field to the atom, then atoms can be polarized and get the induced dipole moment, mu. And this laser interacts with this dipole, then we have an energy shift, which is called redshift or Stokes shift. Dipole interaction is given by this, and we get this result. Energy shift is proportional to polarizability times electric field squared. if the laser frequency is lower than the atomic transition frequency, this polarizability can be positive. And in that case, if you have a laser like this, then the atom can be trapped at the intensity maximum of the laser field. This is called laser tweezer. And when you have a standing wave of light by placing a mirror, then antinode of the standing wave gives atoms a maximum intensity, so the atom can be trapped at the antinode of the standing wave. And this is called optical lattice, which forms an array of atoms. First developed by a Hensch group in 1990s. So our idea is to use this optical lattice for the clock, because the most important thing for building atomic clock is to measure the transition frequency as precise as possible. But this kind of optical lattice perturbs ground state energy in this way to trap the atom. And this is very far from the design of the atomic clock. What we thought about is that to confine the atom, and if the laser change the energy of the ground state, then if we change the upper state energy in the same way, then the transition frequency can remain the same. So this is the idea. To do that, redshift for the ground excited state is given by this, and ground state is given by this. We use the same laser field here. So if you equalize the polarizability for the excited state and ground state the same, then you can cancel out this redshift perturbation. This is the idea. But nobody expects such a scheme should work at the level of 10 to the minus 18. So it was a very challenging topic 23 years ago. So this is our transportable clock, developed almost 7 years ago. We have lasers and optics on a breadboard, which is temperature stabilized but by water cooling. And these are homemade lasers. And this is a main chamber for the clock. We have strontium oven, and this is the atom throwing region, which is about 15 centimeters. By laser cooling, atoms can be cooled down to microkelvin at the center of this chamber. And we roll the atom to the optical lattice. And this is how we trap the atom. Cold atom cloud can be loaded to an optical lattice, and optical lattice transport the atom to this, what we call a blackbody radiation shield, which is a very small copper cylinder and temperature stabilized to a fixed temperature. And this is important to achieve 10 to the minus 18 uncertainty, because we are surrounded by a blackbody radiation here, whose electric field amounts to 8 volt per centimeter, which is quite large. And atomic energies are shifted by that electric field. So to reduce or isolate the atom, we need this kind of chamber. So this is when we demonstrated the transportable clock at the Tokyo Sky Tree, which is a broadcasting tower in Tokyo. This is our first field demonstration of our clock. So these guys carefully moves our clock to a 450-meter high small room. We learned a lot of things from this demonstration. In the beginning, we are annoyed by a lot of vibrational noises because 3 subway lines are very close to the sky tree. And we have a huge temperature change. In the daytime, they keep a comfortable temperature of 20 degrees Celsius. But at night, when there is nobody, then in winter it's 10 degrees and in summer 30 degrees. So it's a kind lot of temperature difference. So anyway, we set one of the clock at the ground floor and the other clock at the observatory floor at 450 meters and connect these 2 clocks and compare the frequency difference of these 2. This is a very small room we rent for this experiment, and we packed all clock components in that room. And this is measurement. On the ground floor, we put one of the clock, and at the observatory floor at 450 meters, we put another clock. And we measure gravitational redshift by these 2 clocks, which amounts to 21 Hertz. So in this experiment, we wanted to verify how the gravitational redshift agrees with the geopotential difference of these 2 clocks, as I explained in our previous slides. So, in collaboration with Geospatial Authority of Japan, they measured gravitational acceleration and height difference between the clocks, and they determined this geopotential difference very accurately. And we got the agreement of 10 to the minus 5, which is very competitive to the space-borne experiment. Combined with the satellite experiment, we can say gravitational redshift is verified at the 10 to the minus 5 level in this huge range. The most important thing is that this is the first demonstration of 10 to the minus 18 accurate clocks outside the laboratory. And this is a very important step for the future applications. So this explains the power of optical clocks. So far, the test of relativity use space-borne experiment, such as satellite. When we were performing our experiment, European group reported that using Galileo satellite launched into a elliptic orbit accidentally, and as a result, they have a height difference of 8,000 kilometers. And using this 8,000 kilometer difference in the elliptic orbit, they demonstrated the gravitational redshift at the 10 to the minus 5 level. So compared to that, our experiment used just 500-meter height difference. But because of clock's precision, which is about 10,000 times higher than this satellite experiment, we obtained a competitive result for testing relativity. So, the clock application in the future can be to replace the height reference point by clocks. And for this purpose, dissemination of clock signal is very crucial. And for that purpose, we routinely use optical fiber link to compare optical clocks. The serious concern is the Doppler shift. In the optical lattice clock, we confine the atom in a lattice in about 10 nanometer region. And this tight confinement quantizes atomic motion. And Doppler shift can be eliminated. But if you compare this clock and the other clock, relative motion of these clocks will give you Doppler effect. To compare at 10 to the minus 18, relative velocity should be less than 0.3 nanometer per second, which is a very severe requirement. And if you compare these clocks connected by fibers, then this fiber length change should be also this one. For this purpose, we make a microson interferometer to detect the length change of these fibers, which is called Doppler noise cancellation scheme. And we apply this scheme for every fibers that we use. So by applying that technique, we connect our clocks at the University of Tokyo and Riken, which is just 15 kilometers apart, very close. And we measure two clocks at Riken, which was on the same optical table. Because there is no height difference, these two clocks agreed at this level here. While when we measure the university clock, then university clock ticked slower by 700 millihertz, which is because university lab is lower in height by 15 meters compared to a Riken laboratory. So this is the first demonstration of centimeter level relativistic geodesy or chronometric leveling. At this point, the two clocks are so close, 15 kilometers. Tidal effect was occurring in phase and cancelled out. But the thing is, if you make a longer link, then you will see the effect of tidal shift. Remote clock will see softness of the Earth. So, 2-3 years ago, we planned an experiment to connect our clock at Tokyo to Mizusawa area, which is 500 kilometers north from Tokyo. The initial motivation was to see gradual uplift of this area. We had a big earthquake in 2011 in this Tohoku area. At that point, the ground level subsided by as much as 30 centimeters. And now, the ground level is gradually uplifted every 3 centimeters every year. So if you have a 10 to the minus 18 accurate clock, we can measure this slow uplift of the ground level. This was the first idea. And because the distance between the clocks is so large, 500 kilometers, we have also a tidal shift. And we are now trying to see this effect by clocks. And this is a calculation for the tidal effect between 500 kilometers, Tokyo and Mizusawa area. And in a good day, which occurs at the full moon or new moon, they have, if the moon and Earth and Sun align in a line, they will introduce a larger amplitude for the tidal effect. So in these good days, we will see a 5 centimeter change in 6 hours. So this is a good test for the clock stability. So the experiment is now running, and this is a very initial experiment. This measures the beat note between the clocks over 500 kilometers. And we saw a faint change of 3-4 times 10 to the minus 18 over 6 hours. So we are now hunting every small noises containing in this experiment. And I hope we can show you better data soon. So I will change the topic a bit. So we want to make a very compact and stable optical clock. So in the age of cesium atomic clock, the stability goes like this. In a day of measurement, they can see 10 to the minus 15 uncertainty. But by improving the carrier frequency from the microwave to optical. Then a single ion clock can do better, and we expect by averaging for 10 days, we will see 10 to the minus 18 regime. And with optical lattice clock, by increasing the number of atoms, we can do it in a shorter period. Still, we take 3 days. And this stability mainly dependent on the stability of a low noise laser. In our case, we use a 40 centimeter long cavity and make this low noise laser, and we get this. But the 40 centimeter long cavity is so large and delicate, and we want to do it in another way. By preparing just a few centimeter cavity, which gives you a noise level 1 order of magnitude larger, which is given by a thermal noise of the cavity. But if the stability improves as 1 over tau instead of square tau, then we can expect 10 to the minus 18, 19 region in a reasonable aberration time. This is the thing we are very interested in these 2-3 years. So the idea is that conventional atomic clock worked sequentially. Prepare cold atoms and measure its transition frequency. And frequency average is given by square root of the measurement time. So even if we use optical lattice clock, and if we use a compact cavity, the stability follows this line, and there is no gain in using many atoms. So our new approach is to continuously measure and control the frequency of clock laser. If you continuously measure, then the frequency uncertainty scales as 1 over tau. And we expect this kind of stability until quantum noise dominates the measurement. And for this purpose, we thought about the modern spectroscopy on atomic beam. So there was an old cesium beam machine, and similar beam experiment can be done optical Ramsey scheme. The drawback for this optical Ramsey spectroscopy on atomic beam is that there is residual Doppler effect and some other effect. If we have lattice-trapped atoms for this beam spectroscopy, there should be no residual Doppler effect, and we will have accurate measurement of transition frequency. And we proposed longitudinal spectroscopy using optical lattice. An important component to realize the idea is continuous source of lattice-trapped atoms. We recently demonstrated such atoms. We could entrap the atom in this region, and we extract that atom continuously by moving optical lattice in this way. Then, applying another moving optical lattice in this way, we redirect the atom to the different direction. This is cartoon what we are doing. We transport the atom by a moving optical lattice, and this atom moves to the upper right direction. The idea is that while you apply laser cooling, there are many scattered light from laser cooling. But the light goes straight. So if you change the direction of atom, then this unnecessary light can be blocked by a wall. So if you apply this region for a new clock spectroscopy region, then you will realize a continuous operation of clocks. I will briefly mention our effort to compare our clock to a European clock with a transportable clock. In Europe, they have a huge network of optical lattice clocks. With fibers, they connect German clock to Paris and to Teddington, and also to Inlim. So if we take our clock to one of these institutes, then we can compare our clock and European clocks. That was the idea. So we shipped our clock by a wooden box last year, February, and it arrived at the National Physical Laboratory in Teddington. This way. And we unpacked it and operated. It was a very quick experiment. So Takamoto and Ushijima operated the clock in a proper way in about a week. Then after the campaign at Teddington, they transported our clock to PTB in Germany. And experiment was successful. We operated mobile clocks in Europe, and we are now checking the international agreement of clocks. And to push this kind of experiment further, we learned many trials are necessary. And to do that, commercial reference clocks would be helpful. So I will introduce our project in collaboration with the industry partners to make a commercial clock. We think about new design and very accurate clock, and also think about new applications. And these companies, Shimazu and GL, make a physics package and electronics and lasers. And NTT, which is a telecom company, provide us a fiber link. And they also think about their business. This is a photo that we work to build our clocks in our lab. This is laser electronics package, and this is physics package. And I will show you a movie. This is a second generation physics package. It's in a box of 50 centimeter one side. You will see a laser-cooled atom here. And further cool the atom and load to the optical lattice, and we interrogate it. This is the whole system. Lasers and electronics are here, and we have physics package, and we have small cavity. When we compare this machine to our Sky 3 machine, the stability goes down to 10 to the minus 18 level in about 3 hours. So from the viewpoint of stability, it's good. And we are now checking the uncertainties for this clock. Then this is a table for the transportable clocks worldwide. Our Sky 3 machine occupies a volume of 1,000 liter, and uncertainty is mid 10 to the minus 18. And our new machine is almost 1/4 in volume. And we expect a similar or better uncertainty. So, such transportable and accurate clock will alter our view of space-time. The clock will be further downsized and more robust by a continuous interrogation scheme. And if we combine our clock oscillator and the counter, then we can make a portable standalone clock, and which is in scope. Our mind is still in the age of absolute time in Newtonian mechanics. So we expect clocks should be synchronized. But in a future clock, future standalone clock, it's natural that this clock and this clock give different time and or frequency, because these clock will reveal relativistic space-time that depends on the, for example, gravitational potential difference or velocity of the observer. So by making this standalone clock, the clock should be a sensor for curved space-time. For example, if we combine such standalone clock and, for example, Google timeline, and if we drive with the mobile standalone clock, start lab at t equals 0, and drive highway, then clock delays by a special relativity. And if you drive up to the mountain, then time advance because of gravitational potential. And go back to laboratory again. Then the clock accumulates relativistic time. And you will see that your colleague should look a bit younger. So making a clock was a national strategy in the past. The clock was invented, and GPS system started, and civilian use of GPS broadened the application of GPS. And Google Map appears, and automatic driving is now in reality. Nobody think about the usage of accurate clock. Optical lattice clock was proposed more than 20 years ago, and now we have a compact clock, and they should be commercialized very soon, and new definition of second may happen. Then we can explore relativistic space-time by such clocks, and we need to think about strategy to how to use it. Important thing is to find a new target that new optical clock can only access. So there are conventional microwave clocks. And optical clock will improve its accuracy. But important thing is to find that optical clock only see something. Applications that the optical clock are mandatory. And relativistic geometry is one of the examples that optical clock can do it. So this is a group we are working with. So many students and experts like Takamoto and Ushijima push your work so hard. And this is a summary. So optical lattice clocks demonstrate that is melting clock that see curved spacetime on a daily scale or our personal scale. And we can expect a game change by applying a continuous interrogation of atoms. Then we want to dream about the future applications of clocks. By connecting clocks, then these clocks will be a sensor what is happening underground. Thank you very much for your attention.
Thank you so much for your talk, Professor. The floor is now open for questions. Anyone who has questions, just raise your hand and wait for the microphone to get to you. Thank you.
So, Professor Katori, thank you very much for this wonderful talk. In your experience, so in the past with the season clocks improves about 1 order of magnitude per decade.
Yes.
Now optical clocks are going 2.5 orders of magnitude per decade.
Yes.
So my question is, from now to the future, how much will improve the accuracy of atomic clocks. So now we are at 10 to minus 18. Can we reach 10 to minus 19, minus 20 with optical clocks? That's my question.
Thank you very much for a very good question. So, in terms of accuracy, it's not so easy to improve. Until 10 to the minus 18, it was quite straightforward to improve accuracy in optical lattice clock. And so there are a lot of sources of uncertainties, such as blackbody radiation shift, as I mentioned, and higher order effect of light shift and atomic collisions, and these will appear at 10 to the minus 19. So, in this case, by using a blackbody radiation shield, the clock uncertainty can be in the 10 to the minus 19 in terms of blackbody radiation. But if you say it at 10 to the minus 20, it's not so easy. So, we can demonstrate the stability of clock at 10 to the minus 20, 21, as demonstrated by Junier's group. But they just demonstrate stability. Stability can be improved by preparing many atoms or good lasers, but accuracy is a very important aspect of atomic clock, and we need to be careful to state the accuracy at the 10 to the minus 19 level. So we are now improving the stability by a continuous measurement scheme. Improve the stability to improve as Mandover tau. So we are doing this because by improving the stability, we will verify the sources of uncertainties better at the 10 to the minus 19 region. Then we can investigate what would be the serious sources of uncertainty at 19 region. Then we can go to the next step. So now I think it would be a time-consuming task to improve the accuracy. So I hope to push further, but the speed of progress would be almost saturated at the level of 10 to the minus 19 or 18. So I think it's a good timing for the definition. And so we are also trying nuclear clock. And in a very optimistic viewpoint, nuclear clock can be more accurate than optical lattice clock because the nuclear transition is well shielded by an electron cloud. But even in the case of nuclear clock, to think about the accuracy of 10 to the minus 19 is not the easy thing. At that point, the motion of atom may be one of the reasons for the uncertainty. If the ion moves in an ion trap, it will give a time dilation shift, and it's not easy to control at the level of low 10 to the minus 19. So, so I will say the progress of accuracy will be such.
Very interesting talk, and always at the edge of physics, we have some fundamental questions. We don't know how to quantize gravity, and we don't know how to gravitize quantum mechanics.
Yes.
So that's a very, very important
Yes.
problem to resolve, and it's
Yeah.
going to affect whatever you do.
Yeah.
So the language of the presentation is a classical language, right? So when
Yes.
you calculate the precision on frequency, all the coefficients, the polarizability and G and delta H and C squared, they all depend on the constants of physics. And these constants, we are not sure because they're empirical. They're given a priori, so they're empirical. So they depend on the measurements and the type of experiments that can be conducted to calculate them. And all these constants are going to affect the way you calculate your frequencies, no matter whether you go to a nuclear clock. In fact, in the nuclear clocks, the calculations are more difficult to handle because you start having quark-gluon plasmas in there, and you're gonna run into all sorts of difficulties.
Yeah.
Now, the question is clearly you just answered. Is you're going to reach a plateau like the gravitational detectors. They also have 10 to the minus 18 accuracy for gravitational waves, like the interferometers. So the question, if you want a portable clock, and you know how accurate, if 10 to the minus 18 is not sufficient, clearly what you want a clock, you want a quantum clock, or a clock that is not classical, because the moment you're going to have to treat your clock like a quantum object, because otherwise you will not get the precision. The classical precision is going to be limited. So whatever is going to be available to us is a classical clock with a classical precision, not a quantum precision. Would you agree on that?
What do you mean by quantum precision? So I describe, for example, gravitational redshift in a classical way, but and of course we want to explore these quantum and relativity merges, as you said. But so my question is, what do you mean by quantum clock?
Time does not appear. And that's where the difficulty in quantizing general relativity is. Yeah. So we, in fact, what is saying, we don't know what time is, right?
Yeah.
And we are measuring classically something. It's like what Penrose says. What is time is what clocks measure, right? So you're giving a definition of time from a philosophical point of view because you have an instrument that ticks, whether it's frequency, precision, or whether it's a mechanical hand that moves around the circle. So you're giving a definition to time. So if you can define time, and you put it in the context of a curved space-time, then we should be able to quantize gravity. Because then, you know, curved space-time, now every point where you put a clock, that clock is telling you about something that you can quantize, which would be time in that case.
Yeah.
So, I advise to continue maybe this discussion afterwards as we are running low. I will just let Amitava ask a final question in name of Commission A, and then we will close the session.
Professor Katori, thank you very much for a very fascinating talk. I just have a
very trivial question. You say that your portable clock, or whatever, the best clock that you have, reaches the accuracy for an averaging time of 3 hours or so. Is there any, 3 hours is short, but probably you'd like shorter. Is there a way in which you can make it even shorter averaging time? Or is that the limit?
So, in a transportable clock, so as I said, so the stability depends on the noise level of laser. So, in this transportable clock with a small cavity, the cavity determines the stability. And because the cavity stability is at around 1 × 10 to the minus 15 at 1 second, it will take 10 days to average down to 10 to the minus 18. So the standard laboratory will have their own good cavity. So if you connect this small clock to that good cavity, then you will measure 10 to the minus 18 in 3 hours. So the idea for the continuous clock is to bridge the difficulties, even with a compact cavity that is installed in a 200-liter machine. If we allow continuous measurement, and if the stability improves as 1/tau, then we can go down to 10 to the minus 19 region in 3 hours.
Professor Katori, thank you so much. Unfortunately, there is no time for more questions. We are already over time, so I advise anyone that wants to address Professor Katori to come and talk with him afterwards or in the venue. In name of Commission A and as early career representative, thank you so much for being here, giving this insightful talk. Let's thank Professor Katori.
Thank you very much.